Welcome to this lecture series in linear algebra. In this lecture, we'll prove a key theorem, which is at the foundation of all linear algebra. And let us recall the main ingredients. So we need to know the definitions of linear independence, basis, finitely generated vector space, and the fact that every finitely generated vector space has a basis. So let me not get into the details of these things. One of the main key facts that we need to know is this, which was given as a problem previously. It is very simple and straightforward. It says that if we have a vector space V over some base field F, and we have a linearly independent list. So when I say V1 up to V1 are linearly independent, it just means that this list is linearly independent. Then for any arbitrary vector V in the vector space, we have V belongs to the span of V1 up to Vn if and only if the appended list is linearly dependent. So it's a very simple fact, but we need to know this. All right. So let's move on. Here are some problems for practice. This involves polynomials, so you may skip it if you are not comfortable with polynomials just yet. But rest of the problems are kosher. And now let us move on. So here is the main fact, which is the basis of all linear algebra. It says the following. Fix a finitely generated vector space. So there is a finite subset of V which spans V, and we have F as the base field. Suppose V has a basis of size n. N is some positive integer, and since it is finitely generated, there is some positive integer such that V has the basis of that size. So suppose n is such a thing. N is a positive integer such that V possesses a basis of size n. Then any linearly independent list of vectors that one can form using the vectors in V has size at most n. So once we have found a basis of some size, one cannot find a linearly independent list of size greater than that. That's remarkable, but it's not also very, very easy. It is easy to see this in small dimensions like R2. In these concrete spaces, you can see this in action, no problem. But a formal proof, the proof that we are going to write is not based on any geometric ideas. Not by my light anyway. So now let's get into it. But what I will do is, I will not present the proof in full generality. I will try to expose the main core idea of the proof via a small value of n, and then I will show to you the full general proof which you can read. So I will show the proof for n equals 2. So let this be a basis of V, right? Our hypothesis is that V possesses a basis of size n. We have assumed n equals 2. So let this be a 2-element or size 2 basis of the vector space. And assume on the contrary to the lemma that there is a linearly independent list U1, U2, U3 in V. So there is a linearly independent list of size strictly greater than 2 in the vector space, and we have called it U1, U2, U3. If the size was greater than 3, then we could just chop off the list and retain 3 of the elements of the list. So we want to produce a contradiction. That is our goal. Okay. Now, note that V1, V2, and U1, this list is linearly dependent. Why is that? Why is this linearly dependent? Recall the main thing that we discussed in the opening. This is a linearly independent list because this is a basis, first of all. And this is a spanning list because this is a basis. So u1 is in the span of those two vectors. And since this is a linearly, well, we don't even need to say that. So since u1 is in the span of these two vectors, this list must be linearly dependent. Right? Because you can write u1 as a linear combination of v1 and v2, and therefore this is the linearly dependent list. Very simple. So say alpha 1 v1 plus alpha 2 v2 plus beta 1 u1 is 0, where not all of these things are 0. So where not all of alpha 1, alpha 2 and beta 1 are 0. That's what it means for the list to be linearly dependent, that there exist such scalars. A non-trivial linear combination is 0. Okay. So again, note that beta 1 cannot be 0. Why? Because if beta 1 were 0, this is gone, this is 0. So we would have alpha 1 plus alpha 2, alpha 1 v1 plus alpha 2 v2 is 0, which means a linear combination of v1 and v2 is 0. But since v1 and v2 are, they form a basis and hence are linearly independent, the only linear combination of v1 and v2 that gives 0 is the trivial linear combination, and hence alpha 1 and alpha 2 would also be 0. And therefore this thing wouldn't be true anymore. So if beta 1 is 0, then alpha 1 and alpha 2 are also 0, and hence we would have a contradiction to this, to the choice of alpha 1, alpha 2 and beta 1. So beta 1 is non-zero. Alright. Now, at the same time, not both of these two things can be 0. Also, not both of alpha 1 and alpha 2 are 0. Why is that? Again, if we assume that alpha 1 and alpha 2 are both 0, then that means beta 1 u1 is 0. But u1 is a non-zero vector. Why? Because it is part of a linearly independent list. So no vector in a linearly independent list can be 0. So u1 is non-zero, and hence it would force that beta 1 is 0. So if both of alpha 1 and alpha 2 were 0, then beta 1 would also be 0. And again, we would have a contradiction to the choice of alpha 1, alpha 2 and beta 1. So this is also true. I'm not writing the reason, I have said it. So say alpha 1 is non-zero. Doesn't really change the argument. If we assume alpha 2 is non-zero, the same argument will go through. Necessary notational changes will be required. Okay, so therefore, v1 is in the span of v2 and u1. Why is that? Because v1 is equal to minus alpha 2 by alpha 1 v2 minus beta 1 by alpha 2 u1. Right, this is legitimate because, what have I done? This is alpha 1. This is legitimate because alpha 1 is non-zero. So we have just shuffled things around and we get this equation which shows that v1 is in the span of v2 and u1. Okay. Therefore, this further implies v is span of v2 and u1. So why is this? Well, v2 is already in the span of this, clearly, and v1 is in the span of this, as we showed. And since v1 and v2 together span the entire vector space, because this is a basis, we must have that the span of this is the entire vector space. So we have that. And again, this implies, therefore, v2, u1 and u2 is linearly dependent. The reason is U2 is in the span of the first two, as we just showed. So this is a linearly dependent list. Unfortunately, I have to go to a different page. So therefore, there exist scalars, let's call them delta 2, gamma 1, gamma 2, such that delta 2v1, or what have I written, delta 2v2 plus gamma 1 u1 plus gamma 2 u2 is 0, and not all three of the scalars are 0. Right? This is immediate from this statement that this list is linearly dependent. Okay. Again, this implies, therefore, delta 2 is non-zero. Why? Because if delta 2 were 0, then we would have this linear combination of u1 and u2 is 0, but u1 and u2 are linearly independent, and hence it would force that gamma 1 and gamma 2 are also 0, contradicting the choice of delta 2, gamma 1 and gamma 2. So delta 2 is non-zero. And again, this implies v2 is in the span of u1 and u2. Just shuffle around this equation like we did the last time, or maybe I'll write one line. The reason is that v2 is equal to minus gamma 1 by delta 2 u1 minus gamma 2 by delta 2 u2. So we have v2 is in the span of u1 and u2. Okay. Now, therefore, v2 and u1 are in the span of u1 and u2. Why? Because we showed v2 is here and u1 is clearly here because u1 is sitting here. So we have that, which implies span of v2 and u1 is contained in span of u1 and u2. But what is span of v2 and u1 together? Look at the last page. Span of v2 and u1 together is v, so this implies the entire vector space is contained in span of u1 and u2. But the reverse containment is obvious, and therefore v is equal to span of u1 and u2, which implies in particular that u3 is in span of u1 and u2, which implies u1, u2, u3 is linearly dependent. And this is a contradiction to the choice of u1, u2 and u3, and we are done. So this is a contradiction, and that finishes the proof. It's a very nice proof, and you can generalize it to any n. I have written all the details here. This is the first page of the full general proof, and this is the second page of the full general proof. You can pause the video and read it. Okay, so let's move on to some conclusions that we can draw. So first thing that we can deduce from here is that any two bases of a finitely generated vector space have the same size. Here is the proof. So let B and B prime be two bases of the vector space. First, think of this as a basis and this as just some linearly independent list. So the size of this is at most the size of that. And now reverse the roles. Think of this as a basis and this as just some linearly independent list. So the size of this is at most the size of that. So these two things give you that B and B prime have the same size. So dot dot dot, you can fill in the details. There is nothing to fill anyway. So these two bases must have the same size, and we have this remarkable and beautiful property that any two bases of a finitely generated vector space have the same size. Okay, so now we can define something by the virtue of this theorem. We can now define the notion of dimension. So let V be a finitely generated vector space. The dimension of V is the size of any basis. Since it is a finitely generated vector space, it has a finite basis. Just take the size of that. That is defined as the dimension of the vector space. This is well defined by virtue of the previous theorem, because no matter which basis you pick, it will have the same size. Okay, and therefore from now on, we will not use this phraseology. So finitely generated vector spaces will be the same thing as finite dimensional vector spaces. Right? So when we say finite dimensional vector space, we mean the same thing as this. But this is the terminology or rather the phraseology that you see in textbooks and in any exposition. So now we will use it without any confusion. Okay, there was something else that I wanted to say. Yeah, so this entire lecture series is about finite dimensional vector spaces. We will not be dealing with infinite dimensional vector spaces. That is the subject of functional analysis rather than linear algebra. Okay, so here is a corollary to our main theorem. Fix a vector space V over some base field F, B be a basis of size n, then any linearly independent list of size n is also a basis. What our main lemma says is that any linearly independent list has size at most n, but this says that as soon as you have a linearly independent list of size same as the size of any basis, then that linearly independent list must also be a basis. Very nice. Proof is also very simple. So fix a basis, we have already a basis of size n, so let this be a linearly independent list. We want to show that this is a basis. So want to show that this is a basis. Okay, suppose not. Now the only reason why this couldn't be a basis is that this does not span the entire vector space. So then span of these n vectors is strictly contained in V. So now we can find something in V that is not in the span of these vectors. But then this list of size n plus 1 is linearly independent. Because this was already a linearly independent list, we have appended something that is not in the span of the first n, and therefore this will be linearly independent. This is very simple because if you just assume this is linearly dependent, you will write a linear combination which is 0, and you will see that the coefficient of V first of all cannot be 0, and then you can write V as a linear combination of the first n and have a contradiction. So please justify this for yourself. And now we have a contradiction to our main lemma, because now we have a linearly independent list of size greater than the size of the basis. And therefore, our assumption that this is not a basis must be false. So any linearly independent list whose size is same as the dimension of the vector space must be a basis. Very nice fact. Okay. Let's see some examples. well, only 2 examples. So Fn, what is an example of a basis of Fn? We have already seen this. So E1 is this one, E2 is this guy, and up to En. So this is a basis. And therefore the dimension of Fn, this is how we denote dimension of any vector space. We write dim. So dimension of Fn is n. We have a basis of size n, therefore dimension of Fn is n. What about this guy? So say, so here x is finite. Let's say x has size n. So now we will write down a basis of it. So say, or rather for each x, define the function delta x from x to f. So here f is just any field. So delta x is a function from x to f defined as delta x of y is 1 if y is equal to x, 0 otherwise. Okay, that is delta x. And say x is this set of n elements. Now for any function f, so clearly delta x is a member of this vector space. Now for any function in this vector space we have, and this is something you can easily check. Is equal to that, and in a more convenient notation it is written like this. This is just a triviality, this is statement. So therefore f is in the span of these n vectors, and in fact these n vectors are linearly independent. So finally this is a linearly independent list. Why is that? Just assume some linear combination vanishes. If this vanishes, then what does that mean? This as a function vanishes on every point of x. Substitute x1 in place of it, you will see that alpha 1 must be 0. Substitute x2 in place of it, you will see that alpha 2 must be 0, and so on. So everything must be 0. And that's it. So this is a linearly independent list. This is also a spanning list, as we just argued, and therefore this is a basis. So the dimension of this space is same as the size of x. Okay. So this is what we have shown is that dimension of this space is the cardinality of x, where we are assuming that x is a finite set. This is a finite dimensional vector space, and its dimension is just the cardinality of the set x. Okay, so now we can move on. Okay, so bases and subspaces. Fix a subspace, or rather fix a vector space V, then any subspace of our vector space, or any subspace of a finitely generated vector space, is also finitely generated. This is something that must be intuitively obvious, but somehow perhaps it's not immediate from definitions. Maybe it is, but I don't see it, at least as of now. So we want to show that if we have a finitely generated vector space, then any subspace of it is also finitely generated. So let's start. Let V be a finitely generated vector space, or a finite dimensional vector space, as we know they are the same thing. Say dimension of V is some n, meaning any basis of V has size n. Let U be a subspace of V. Okay. And assume on the contrary that U is not finite dimensional or finitely generated. we want to produce a contradiction. Okay, so how do we do it? So first let u1 in u be non-zero. So since u is not finitely generated, we should be able to find a non-zero vector in it, because if 0 were the only vector in u, u would be finitely generated. Okay, so we have a non-zero vector in capital U. Again, since u is not finitely generated, span of u1 is not u, so we can find u2 in u such that u2 is not in span u1. Right? The reason is very simple. Why should such a u2 exist? The reason is that span u1 is not the entire u. That's it. So we can find some other vector u2 which is not in span of u1. u2 again lying in the subspace capital U. And we can continue. So now we will find u3 in capital U such that u3 not in span of u1 and u2, and so on and so on. We will find n plus 1 such vectors. The point is that, the upshot is that the list u1 up to un plus 1 is linearly independent. So how do we see that? Well, first of all, this list, the singleton list, is linearly independent simply because u1 is non-zero. Now, since u2 is not in the span of u1, this two-element list u1, u2 is linearly independent. And again, since u3 is not in span of u1 and u2, the three-element list is linearly independent. And if you just continue this reasoning, you will find that this is a linearly independent list. And hence this is a contradiction, because no linearly independent list can have size greater than the dimension of the vector space, as we proved in our main theorem. So this gives a required contradiction. And we are done. So any subspace of a finitely generated vector space is finitely generated. Okay. We will now prove an extension theorem that any linearly independent list can be extended to give a basis. So fix a vector space V which is finite dimensional. Suppose we have a linearly independent list in this vector space V. Then there exists some list of vectors such that if you append them to our original list of linearly independent vectors, then you get a basis of V. So all of this is trying to say that any linearly independent list of vectors can be extended to a basis. Okay. So here is the proof. Say dimension of V is n. Now if this were a basis, then we are done. Is already a basis, then we are done. If this is not a basis, then what does that mean? It means that the span of this list is not everything. So if not, then let u1 in V but not in the span of these vectors. Okay. But then this means that we have a bigger linearly independent list. And just keep growing this list in the same fashion. At some point you will have a linearly independent list of size n. N is the dimension. And that must be a basis. And that's it. So any linearly independent list can be extended to form a basis of the vector space. Very nice thing. And I think now we are at the end of the lecture. We want to show that if we have a subspace U of a finite dimensional vector space V, then the dimension of the subspace is at most the dimension of the parent space. So subspaces are smaller in some sense, in the sense of dimension. And the reason is very simple. Reason is the previous proposition. Fix a basis of U. A basis of U is a linearly independent list in V in particular, and hence it can be extended to a basis of V. So a basis of U can be extended to a basis of V, and hence the size of any of a basis of U is at most the size of any basis of V, and hence dimension of U is at most the dimension of V. That's all. So I've said it in words, you can write it down. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.